So today we'll discuss an important fiber optic device known as fiber Bragg grating. Or FBGs for short. Right, so you must have heard about Bragg gratings and Bragg reflection already in your basic physics courses even in high school and bachelor's, right? For example, when we scatter X-rays to study the crystal structure of the material, right? There is Bragg reflection going on due to the periodic arrangement of the atoms. So basically, Bragg reflection occurs whenever there is some periodic change in some property like refractive index or density or something, right? And you have some electromagnetic wave incident which sees this periodic structure, right? So this periodic structure is also known as a grating. And basically, what happens is that due to this periodic structure, so you can imagine like there is some small reflections going on from each of the small portions of the periodic structure, and at some particular angle, all of these reflected waves constructively interfere, and you get a strong reflection at some particular angle, depending on the wavelength of incident electromagnetic waves, and then this period of the grating, right? So you know that Bragg condition. So the similar concept is used in optical fibers, right? To make, for example, optical filters or mirrors for like inline fiber mirrors for specific wavelengths. So specific wavelengths can get reflected, other wavelengths will be transmitted, right? So you can make optical filters, and so you can use this for various applications. So fiber gratings are used widely in various places. So we'll study their basic operation, right? So basically, as the name suggests, so you have an optical fiber, right? So you have some core region here with refractive index N1, and then a cladding region with refractive index N2, right? So that's, so for example, the bare step index fiber, right? So what one can do, so typically this core region is doped, right, to make N1 higher than N2. So typically, as we've discussed previously, so for example, this is doped with germanium, some percentage depending on what index difference we want. And so then people found out that if you have this germanium doped glass and you expose it to UV light, okay, so ultraviolet light, then basically if the light is intense enough, then what happens is that actually you can change some of the atomic structure here, and you can change the refractive index slightly wherever you expose it to ultraviolet light of strong intensity. Okay. So people realize, yeah. So for example, let's say you incident UV light. Okay. So imagine two plane waves sort of incident at from two different angles. Let's say the angle between them is theta, right? So this is UV light. So it has some wavelength lambda UV, right? So UV means like the wavelength is typically less than 400 nanometers, right? 200 to 400 nanometers, that would be the range of this UV light. And this works best typically for shorter wavelengths. So typically, for example, this UV light is typically in the range like maybe 250 nanometer or typically 200 to 300 nanometer. Okay. So let's say you have two plane waves here. So you have so you can do this, for example, if you have, let's say, two sources of UV light here, or you start with one, split them into two, and then recombine. So you have these two plane waves here, so you can imagine when you interfere them on on this fiber here, there will be some interference pattern created, right? So there will be some regions of high intensity and low intensity due to the interference. And so wherever the intensity is high, basically the refractive index changes slightly because of this photorefractive effect that we talked about. So wherever the UV intensity is high, the refractive index increases slightly. Okay. So you get this periodic structure within the fiber core, right? And of course, you can control the period of this grating that is formed by controlling the angle, right? So you change the angle. Of course, the period of this standing wave formed here, the intensity pattern will change, right? So, for example, if the period here is capital lambda, that depends on the angle of this. So it depends on the wave and the angle of this, the two beams interfering, right? So you can check that the relationship is that, right? So if theta is 0, which means that basically both beams are parallel like this, of course there will be no interference, right? So if theta is 0, this period you can see is infinity. So basically there is no grating. And if this theta is, the other limit is if this theta is 180, so they're coming from opposite directions like this. So you know when two beams from opposite directions interfere, then you get a standing wave, right, with this period lambda by 2. Okay, so basically by controlling this angle, we can control the period of this grating which is formed here. Okay, so in these regions, basically you get a change in the refractive index, and typically that change is of the order of 10 to the minus 4, roughly. Okay? So 10 to the minus 5, 10 to the minus 4, that's the sort of the level of the index change that we get, right? And so recall n1 minus n2, the difference is also about 10 to the minus 3. Okay? So the index change here is smaller than the core index cladding difference. Okay. So now you have this. So once you formed, you shine this UV light and you form this grating. Okay. And so you can, of course, control the area over which you shine this UV light. So basically, you have some length L of this grating formed. And so now basically, so you have your fiber, right? And then over some section here, you have this grating formed. Okay, so now imagine, let's say I input some, so some field is traveling here. For example, like the lowest order LP mode is incident here, right? So depending on its propagation constant, right? So again, this period here is lambda, capital lambda. So when you satisfy the Bragg condition, right? So now in fiber, basically there are only two propagation directions possible, right? Either forward or backward. So in the general free space Bragg condition, you know that typically like you have some periodic structure here, and then you can incident light at some angle, and then you get some reflection, right? And then the relationship between this angle of reflection and the period, there's the back condition, right? But here basically this angle, since basically you have a waveguide here, there's only two propagation directions, forward and backward. Okay, so basically this theta you can only have either 0 or 1. Okay? So the Bragg condition for this kind of structure basically would be, so you have a forward propagating mode and then you have a backward propagating mode here, right? So for example, in single mode fiber, you just have the LP01 mode. So either it could be forward propagating or backward propagating, right? So when you satisfy this Bragg condition, when the propagation constant here, so basically, so So the difference in the propagation constant of the incident and the scattered wave is equal to the spatial or the equivalent wave vector for this periodic structure, right, which is basically 2 pi by the periodicity of the structure. Right, so this is the Bragg condition for this case. So if the mode here incident has a propagation constant which satisfies this condition, then you will get a strong reflection. Okay. So basically, again, physically what's happening is you get small reflections from each of these regions where the index has changed, right? So recall whenever a wave goes from a region of refractive index to another region of different refractive index, you get some reflections, right? So you get some small reflections here, and when this condition is satisfied, basically all these reflections add up in phase and you get a big reflection. When this condition is not satisfied, basically these reflections are out of phase so that they cancel out and mostly you get transmitted. Right? So you can see basically this condition for reflection is right, and you know the propagation constant here, beta, we can write as 2 pi over lambda times the effective index. Okay, so you can see that the wavelength which will be reflected, which is known as the Bragg wavelength, depends on the period like that. Right, so it depends on the period of the gradient. N effective, as we know, is roughly between it's somewhere between N1 and N2, and so it's roughly basically the index of silica glass. Right, so N effective would be 1.45, 1.46, something like that. And so, right, so if you want to design a fiber Bragg grating to reflect a particular wavelength, then we know what period of the grating we need. Okay, so the wavelength which is reflected is known as the Bragg wavelength. So, for example, if you take the standard single mode step index fiber, right? So you have carrying index 1.45. This numerical aperture defined like this is about 0.1. Core radius about 3 micron. Okay, so if you take these parameters, basically the fiber acts as single mode for wavelengths greater than 784 nanometer. Okay, so at this wavelength, basically the V number is 2.4048. For wavelengths longer than that, the V number is smaller than 2.4, so it's single mode for those wavelengths. So, for example, we can take a wavelength of 850 nanometer. Okay, so the effective index for the LP01 mode for at this wavelength comes out to be about 1.4517. Okay, so then if I want to reflect this particular wavelength 850, then the period that I need is so lambda by 2 n effective, right? So that comes out to be about 290 nanometer. Okay, so you can see that the period of the grating needs to be typically it's much smaller than the wavelength. Right, so to reflect 850 nanometer, I need a grating period of about 290 nanometers. So that's also where UV light helps, right? Because the wavelength of the UV light is in this range, so we can make gratings of that period. Okay. Right, so that's basically sort of the basic mechanism by which these fiber Bragg ratings work, right? So, so for a particular period, it will reflect that particular Bragg wavelength strongly, and other wavelengths will be sort of transmitted. So let's analyze this structure a bit more rigorously using again this sort of coupled mode theory that we use for the directional coupler, right? So again, basically what is happening is this structure here is coupling the forward propagating mode to the backward propagating mode, right? So in the directional coupler, we had two different modes and two different fibers or waveguides which were coupling to each other. Here we have only one fiber, but the two modes which couple to each other are the forward and backward propagation. So we can use a similar coupled mode theory to analyze this. Okay, so analyze this using coupled mode theory for contra-directional coupling. So basically, we are using the coupled mode theory to see the coupling between waves traveling in opposite directions, right? So that's why it's contra-direction. Recall in the directional coupler case, we were looking at coupling between waves traveling in the same direction. So again, so let's just look at the core region here. Okay, so we have some length L here. Okay, so this is Z equal to 0. So you have some incident wave input light from here. Okay. So let's say this has some mode profile psi1 of x comma y, right? And so in this Bragg region here, basically there is some coupling between the forward and backward waves, and basically the reflected wave traveling the backward direction. So for single mode fiber, there would be only one mode, right? So both the forward and reflected will be LP01 modes, the same mode basically. But in general, we can analyze. So let's say if the fiber supports some higher order modes also. In general, we can analyze the situation where the reflected wave could be some other mode. Okay. So that is also possible, right? As long as you satisfy. So basically, so now your input has some propagation constant beta1, and then your reflected has some different propagation constant beta2. But again, if you satisfy the Bragg condition, which is like beta1 minus beta2, because beta2 is now opposite direction, is equal to 2 pi over this period lambda. Then you could scatter a forward propagating mode into this other mode which is traveling the backward. Okay, so in general, we could consider two different modes, both forward and backward. Okay, so in this region, in the Bragg region here, you have both the forward and so the forward propagating mode is getting reflected, and then the backward propagating mode is building up here. So in this region between Z equal to 0 and L in the Bragg region, we can write the total field, right, as a superposition of the forward and the backward, just like In the case of the directional coupler, right, we had two modes in the two different fibers, and we wrote the total field in the coupling region as a linear combination of the two. We can do the same here. So we write so this is the forward propagating mode, psi1 e to the minus I beta 1 z. So we add that up with some coefficient now, which depends on the propagation distance. And then the other contribution is from the backward propagating mode. Right, so the sign here will flip. So again, the convention that we take is e to the I omega t minus beta z. Right? So forward propagating in the plus z direction will have e to the minus I beta z, and backward propagating in the minus z direction will have e to the I plus I beta z. Okay? So that sign differences. Okay, so this is the input wave, and this is the reflected wave. Right, and again the task would be to set up equations for this coefficient A and B, and then solve and see how the basically the reflection is building up depending on this period and the wavelength, etc. So, so these 1 and 2 are basically the modes in the bare fiber, right? So basically, they satisfy the wave equation for the bare fiber here without the grating. So right, so the psi1 and psi2 satisfy the wave equation in the bare fiber. So n of x comma y is the refractive index profile of this bare fiber. Right, and psi1 has propagation constant beta 1, psi2 has propagation constant beta 2. Right, and again, so this is the transverse part of the del square operator. So x and y, right? The z part gave us this. So now, if you look at the field in the Bragg region, so that needs to satisfy its wave equation in the Bragg region here. So that will be basically that. Again, recall. So the total wave equation is del square plus k naught square n square, right? And the n square in the Bragg region here is the bare fiber refractive index profile, right? Plus this change due to this UV light that we, right? So that now depends on Z. Right? So the refractive index, bare refractive index profile here, so for example, for a step index fiber, this is just n1 square and n2 square for so it only depends on the transverse coordinate, right? But this grating that we formed, of course, now there's a dependence on the z coordinate, right? So this is the Bragg grating, right? So this has some periodic dependence on z. So again, we follow a similar procedure, right? So we take this form for the field as a superposition of the bare nodes, and then substitute into this wave equation that it needs to satisfy in the coupling region, right? And then again we use this slowly varying basically substitute and then use this slowly varying amplitude or slowly varying envelope approximation, right? So basically neglect the double derivative terms of the amplitude here. Right, so this is the total del square, so it will have a transverse component plus the z component, right? So the z component, so we'll have terms like this, which we neglect. We only keep the first order terms, right? Again, we call our discussion on when we were discussing the direction coupler. So same thing here, we say that the amplitudes are not varying too much over a wavelength scale, so we neglect the second derivative terms. So then we are left with okay. So where we've also used these relations, right? So when we substitute this form into here, we'll also get, so for example, the transverse derivative of psi1 and psi2, where and then we can use these relations, right? So some terms will basically cancel out. So we are left with these terms. Okay. After also neglecting these. So, yeah, so the question is what determines the strength of the coupling. So we'll see the expression for the coupling coefficient explicitly. But you can imagine what will decide the strength of the coupling, right? So first is, of course, you have to match this condition, so that period has to be correct. And then how strongly it couples. So this is a grating, right? So there is some index difference happening here between this region and this region. So you can see, imagine that the effect will be stronger if this delta n is higher, right? So there is a if the grating the contrast is stronger, you can imagine that the reflection from each section will be stronger, right? So again, like when a wave goes from a region of index n1 to n2, right, the reflection coefficient sort of depends on the index difference. So larger the index difference, the stronger the reflection, right? So if this change in index is higher, you can imagine that you'll get stronger reflections and the coupling will be stronger. Okay, so we'll explicitly see that actually the coupling coefficient will be directly proportional to this delta. How much index change? Yeah. Okay, and so the delta beta here is beta 1 minus beta 2, so beta 1 plus beta 2. right? So with psi1 we get e to the minus I beta 1 z, and with psi2 we get e to the I plus beta 2 z. So we multiply by e to the I beta 1 z. So here we get delta beta is beta 1. Right. So recall in the directional coupler case, when we were considering coupling between both forward propagating modes, there the delta beta was the difference. So here, since we are considering opposite waves traveling in opposite directions, the delta beta is the sum of the magnitudes of the wave. Okay, so recall, so we had this similar kind of equation for the directional coupler also, right? And to simplify that, basically what we did was, so we used the properties of the mode profiles. So for example, we multiply by psi1 star and then integrate over the cross section xy plane, right? And similarly, we can multiply by psi2 star and then integrate over the cross section plane to get equations for A and B, right? So we can do similar, same thing here. So yeah. So yeah, if you multiply this equation by psi1 star and then integrate over the cross section xy plane, we will get an equation for A like this. We call this. Okay, so this dA by dz is coming from here, right? So we multiply by psi1 star and then integrate. So with dA by dz, we'll get something like integral of mod psi1 square dx dy. So this C11 here, right? So that's coming with A. So A is here, right? So when I multiply again, so multiply by psi1 star and integrate, so we'll get integral of psi1 star delta n square psi1. Okay, so that's C1. So now, since this delta n square also depends on z, right? So this C11 actually is a function of z, because this delta n square depends on z, right? It's a periodic structure in z. In the directional coupler case, we call this delta n square was not depending on z, right? That was this depending on the cross section. So these coefficients here were independent of z in that case. But here, these coefficients are actually z dependent, because this delta n square is now a function of z. Okay, so similarly, you can check. So now C12 is coming from the B term here. right? So that will have integral of psi 1 star delta n square psi 2. C12 will be right. So, for example, if you're doing this in a single mode fiber, so then psi 1 and psi 2 are both the LP01 modes, right? So actually psi 1 and psi 2 are the same. So in that case, this C11 and C22 will C11 and C12 will be the same because psi 1 and psi 2 are the same. Okay, and then we have another third term here, which is coming from d by dz, right? So the coefficient for that I've denoted as C12 prime. So C12 prime you see, so integral, that will be integral of psi 1 star psi 2. So C12 prime so actually this term will be independent of z. Right, because there is no delta n here. So you can see actually there is no z dependence here. Right, so actually this, I can remove the z dependence here. So that's actually a constant. Right? So again now, if, for example, if you are looking at a single mode fiber, then psi 1 and psi 2, the mode profile is the same. It's the same mode. There's only one mode. Right? So then actually the numerator and denominator here are the same. So then in that case, C12 prime is just beta 2 by beta 1. Or again, beta, the magnitude of beta 2 and beta 1 will also be the same in that case. And C12 prime will just be 1. But if we are looking at different modes, then we have to. But anyway, so recall again in the directional coupler case, we had neglected this term, right? Because there, recall psi 1 and psi 2 were the modes in the two different fibers, right? So psi 1 was here, psi 2 was here. So we were looking, so this is like the mode overlap between these two, right? So we said that that is much smaller than these other terms, and so we neglected this third term, recall in that case. In this case also this term will go away, but due to a different reason. Okay, so again, so the major change from the coupling for co-propagating waves, for this counter-propagating waves, is also well, in this Bragg region, is because now the refractive index is z dependent. You have these coefficients also being z dependent. Okay, so again, okay, so if I write this refractive index profile here in the Bragg region. Okay, so it's a periodic high-low region, right? So I can model this as some delta n square in the transverse coordinate, and then a periodic function in the z coordinate. Right. So it turns out that, so recall how this is made is by interfering this UV beams, right? So the interference pattern created is some sinusoidal pattern like that, right? So it's not like a square wave where like you have some region of high index and then another region of low index, but it's like actually a smooth variation. Okay, so actually the refractive index also, because the intensity varies smoothly, the refractive index will also end up varying smoothly, and you can model it like a sinusoidal function like that. So this actually models the actual refractive index profile that we get by shining these UV beams in the fiber core. This models it pretty well. Okay. So where this capital K, right, is 2 pi by, because the period is capital lambda. So right, and so for example, this change in index profile. So typically, basically, what happens is only the core region is changed because that is doped with this germania, right? And the cladding typically is not doped. So only this happens only in the cladding, and if typically basically you shine the whole core region so that basically, yeah. So if you take a step in X fiber, the whole core. So over the entire transverse coordinate, this index change is happening, right? So basically, what I'm saying is, so this you can simply just say this is some delta n square in the core region. So for x square plus y square less than e square, right? And then 0 in the clad. Right? So it's some constant change within the core, and then nothing in the clad. And the z dependence is the sinusoidal periodic. Okay, so if we use this form for the index profile, and then substitute here, so you can see that so basically this integral is only over x and y, right? So the z dependence here, sine kz, will just come out of the integral, right? So this means that C11z I can write as some kappa 11 times the z dependence sine kz. Right, where kappa 11 would be basically, right, so if I substitute this form for delta n square here, so then basically I just get delta n square, it's a constant change, and then basically the integral so only remains in the core, so I get psi 1 star or mod psi 1. So this delta n square is a constant, it just comes out, and I get the integral of mod psi 1 square over the core region, right? Because delta n square is only finite in the core region, 0 outside, and in the denominator I have this mod psi square integral over the whole space, including the clad, right? So you can see this is basically just the confinement factor, right? So this is just the confinement factor. Basically the percentage of the power confined to the core. Okay, so you can see that this coupling coefficient here, kappa 11, depends on the index change, how much the index change is, delta n square, and the confinement factor, right? Because only the part of the mode which is in the core is experiencing this Bragg coupling, right? So that confinement factor comes into picture. Okay, so similarly, so basically C11 has this sinusoidal form. Similarly, C12 will also have a sinusoidal form, right, from here. So C12 I can also write as and 2 times kappa 1, 2, again with sinusoidal sine capital Kz in the z direction. And now kappa 1, 2 sort of similar. Right, so now the integral over the core is for psi 1 star psi 2. Okay, so again, if you have a single mode fiber, then psi 1 is equal to psi 2, right? And then kappa 1, 2 is the same as kappa 1. Okay. And then C12 prime we already saw is just a, it does not depend on Z. Okay, so then this equation, so if I write C11 of Z as some constant times sine Kz, and similarly C12 of Z as some constant times sine Kz, then the equation becomes okay, so basically we just rereturn this equation with these substitutions for C11 and C12. Okay, so now note that okay, so there's an A here. So let's see what these different terms look like. So here the first term, right? So dA by dz is some term times A, and this term is actually sinusoidal in Z, right? So this oscillatory in Z. Okay, so basically it will average to 0 over many periods. So if you look at a length which has many periods here, then basically this coupling coefficient is sort of going positive, negative, positive, negative, positive, negative, right? And so the overall effect when we integrate over the length just averages to 0. Okay. Similarly, this term here, so we have C12 prime is a constant, right? And then this e to the I delta beta z also is sinusoidal, right? I can write it as sine plus cos. So this is also oscillatory in Z, right? And it will again average to 0 or to some small quantity over many periods. Okay, so actually these two terms we end up neglecting because there the coupling coefficients are Z dependent and oscillatory with Z. Okay, and they actually, if you integrate over a length which has many periods, right? So all the positive and negative terms will cancel out, and basically they'll end up contributing something very small, close to 0. Now this third term here, right? So if we write the sine of capital K z as in terms of the exponents like this. Right, so then you'll see that we'll have two terms. One will be e to the I delta beta plus capital K. The other will be e to the I delta beta minus capital K. Right, so again, so if you look at the e to the I delta beta plus capital K term, so now this is also oscillatory in Z oscillating with Z at a fast rate, right? So recall what is delta beta is beta 1 plus beta 2, this is delta beta, and this capital K is 2 pi over lambda. Okay? So actually, to set up this, so we will be looking at wavelengths which are satisfying this Bragg condition or close to satisfying this condition, right? So delta beta will be close to K. Right, so this thing will be like almost like 2 times K. Okay, so it's actually oscillating at a period twice or at a rate or a period which is half the period of the grating. Okay, so it's also oscillating with propagation distance, this term, right? And if you have many periods over this length, this will again average to 0. Okay, so basically there will be only one term remaining here, which is the e to the I delta beta minus capital K. Okay, so again, so e to the I delta beta minus capital K, right? So at the Bragg condition, actually delta beta will be equal to K, so this will be 0. So this will become a constant, right? So that will just give me kappa 1, 2. So what should be? Right? So that will be a constant coupling term, and that won't, of course, average to 0. So that will build up and give me some finite value, right? Or we'll be looking at wavelengths close to the Bragg condition, right, where delta beta is not exactly equal to capital K, but close to it. Okay, so this term will be small. Or in other words, the period of oscillation of this term will be large compared to the period. Okay, compared to the period of the gradient. So it won't vary too much over the length. Like these other terms have periods which are of basically the grating period or twice the grating period or something, right? So they oscillate positive, negative many times over the length. So this term will be 0 or near 0. So basically it will be fairly constant over the length. Okay, so this term will only be the one which contributes. Okay, so we neglect all the other terms and basically end up with just this term, right? So now the propagation of A is coupled to B with this coupling coefficient kappa 1, 2, and then this phase factor. It depends on the wave vector and this matching of the basically how closer to the Bragg condition. Okay, so I hope that's clear. This approximation. Right, and now we can do the same thing to get the equation for B. Right, so start from so we started from taking multiplying by psi 1 star and integrating. You can do the same thing starting with psi 2 star and integrating, do the same arguments, right? End up with some kind of equation like this, and again all the other terms will sort of be oscillatory, only one term will remain. So we'll get a similar equation for B, you can go through the procedure yourself. So you can check that the equation for B will look like this. Okay, so yeah, we have kappa 2 1 instead of kappa 1 2. So because we have psi 2 star psi 1 in this case. But again, if you are using a single mode phi 1 and just looking at the reflection of the LP01 mode, then again psi 1 is equal to psi 2 and kappa 1 2 is equal to kappa 2 1. Right, and again, the only difference is the space factor will have a minus sign here. Here we had a plus sign. Here we get a minus sign. So yeah, just go through the same procedure what we did for A, same thing for B, and C you get this. Okay, so this again. So typically, what is done is basically the modes are normalized such that basically they carry unit power. Or maybe we'll discuss that next class. But so we can write this equation. So this quantity here, delta beta minus capital K, is denoted by this capital gamma. Right. So capital gamma, the value of capital gamma tells you how far you are from the Bragg condition. So capital gamma equal to 0 means you are exactly at the Bragg condition. Right, and okay, so maybe so typically we normalize the mode such that so they carry unit power. So basically, the psi, these mode functions are normalized such that if we integrate mod psi square over the cross section with this constant beta over 2 omega mu naught, we get 1. Right, again, maybe some of you remember that. So when we were discussing the modes and, for example, calculating the power flow, we calculate the Poynting vector, right, E cross H, and then we got the expression for the power flow something like this: beta over 2 omega mu naught times integral of the modes. So this is the electric field profile. So basically, if we normalize the psi such that this quantity is 1, basically that means we are saying that these bare modes are carrying unit power, right? In other words, basically, when we take the total mode as A times psi 1 plus B times psi 2, basically we can directly say that mod A square will give me the power in forward propagating mode, right? And mod B square will give me the power in the reflected or backward propagating mode, right? Because we normalize such that the bare modes have unit power, so their coefficients mod square will directly give me power, right? So if we normalize like this and then use this expression for the kappa 1 2 or similarly kappa 2 1, just flip 2 and 1. So then actually kappa 1 2 and kappa 2 1 I can just write like this. So it's just some change of units because we want to normalize it to unit power. So it still depends on, you can say, delta n square and then this sort of overlap integral. And again, for single mode fibers, basically psi1 will be equal to psi2 and this be the confinement factor, you can say, right? Mod psi square integrated over the 4. Okay, so then basically I can write the equations as this kappa and then I replace this by capital gamma. Okay, so these are the coupled equations I end up with. Okay, so in the next class we'll start from these coupled equations for A and B, right? So there's some coupling coefficient which depends on how much index change happened because of this UV exposure, right? And then the sort of the confinement factor or the mode overlap, and it also depends on basically how far you are from the Bragg condition.